Hello, hello, hello. So we are going to do a video on hybridization. So I'm kind of going to fly by the seat of my pants here, and because I'm used to doing this lecture in person. So I will do my best to make this make sense, because it is kind of it seems like a complicated topic at first, but then trust me, once we get down to the actual bread and butter of it, you're going to go, oh, is that all it is? Okay. So hybridization. So we know carbon, we're just going to start with one that we understand. We all know carbon. Carbon makes CH4, right? So carbon, its valence electrons are 2s2, 2p2. So let's draw that out in a box orbital diagram, right? So fill up the 2s and then one each in the 2p. All right. But how does C bond to carbon 4 times in CH4? So essentially, I'm trying to make CH4, and what kind of bonds are these? These are sigma bonds, right? We established that from an earlier episode, I guess I'll call them. So these are sigma bonds. So this is what carbon looks like. This is what hydrogen looks like. And remember, a bond is 2 electrons. So essentially, I'm going to need to put one here with a hydrogen, one here with a hydrogen, right, and a hydrogen. So that's how it kind of actually looks like when we make a sigma bond, right? I'm circling the hydrogen and the electron that it brought. So hydrogen, which looks like this, 4 of them come together and form a sigma bond. So you can picture it up here in that way, that right here, hydrogen can insert an electron, form a bond. Hydrogen can insert an electron here, but can hydrogen do anything with this? No, it is a full orbital. So what we have to do is called hybridization. A lot of times you'll hear it referred to as the mixing of orbitals. So what we actually do is turn this into all 4 of these. They're now together, and they're now degenerate orbitals. That doesn't mean they stand behind the elementary school library smoking cigarettes. Degenerate means that they are of the same energy. If you remember, 2s is lower in energy, 2p is higher in energy. After they mix, they're all now the same energy, hence why they're in the same block. And what this is called is the sp3 orbital. We'll get into that why in a moment. So what happens is this electron is essentially promoted here. They all face the same way now, and there are 3 or 4 hot spots where a hydrogen can now come in and make a bond, right? So when carbon is bound in 4 different places, we have an sp3. So this is an sp3 hybridization. That's what we just discovered. So then you're saying, okay, well, everything is not just an sp3, Carla. And I say, you're correct. I'm going to pull out a pink paper because I work with what I have around the house. So you say, okay, well, what about, and I messed up a little bit. This is hydrogen single bond to carbon, triple bond to nitrogen. Okay, we're only going to focus on carbon again. But hybridization, again, when we mix orbitals, what happens? So we need 2. How do I know I need 2 places where I have an electron that's pointing up? Well, that's because that's where a single bond comes from. So how do I know I need 2? 1, 2. I only need 2 places where a single electron can come in and create that double bond. What's left over? I have these 2 orbitals left over. What are they? They're p orbitals. So these are actually 2p orbitals. Now what are these called? These are called sp orbitals. Now let's blow your mind real quick, and I'm going to explain why. sp orbitals because it only involves an s and one of the p's. Oh, so we're going to harken back to our first example here while I squeak my chair. Why is this called an sp3? Because the bonding, the sigma bonding, is involved with an S and 1, 2, 3 of the P's. So that's why this is an sp3. Oh, all right, okay. Things are coming together. So this is where we have our sigma bonds. And if you remember from the other one, sigma bonds are the strongest ones. They're the ones that are the single bonds. They're the ones that come first. Okay, but what about the unhybridized electrons here? What do we have from that? These are actually where the double bonds come in. So it looks like we're going to have one double bond, two double bonds. Is that in fact the case? One double bond, two double bonds. It is. So this is how hybridization works, and that's why it's called an SP. So let us, and so this is where the pi bonds come from. So I'm just going to sketch it out nice and pretty. So if you have a SP, what does that mean? That means that we have our, I'll put it A, right? Our atom A. He is bound in how many places? Two single bonds, right? And it's because he carries with him what? One electron from each. Okay? And so we'll just say it's bound to H because H is really easy. H is just, remember, H is just one S. So that's where our single bond comes from, right? I'm making it really pretty, aren't I? So H brings one, A brings one, A brings one, H brings one. So these are our single bonds. Now, what do I do with my, actually, we're doing it to nitrogen, aren't we? Dadgummit. All right, we're gonna erase that. So hydrogen has its one S, right? A has one of these SPs. Let me center this a little bit. A has one of these SPs coming out. They meet together and they form a sigma bond. Over here, A comes out and it meets with one of these nitrogens, right? One of nitrogen's singles, right? So we're only going to focus on actually it is carbon. Oh, you guys. I had a little bit of a rough morning, so if that explains anything. So carbon bound to hydrogen, bound to nitrogen. So these are our sigma bonds. But what happens with these lone pairs? So if we were to draw out nitrogen, we would find that nitrogen has, pull out our periodic table, right? Nitrogen has 5 lone electrons. So nitrogen is 2s, 2p, getting a little messy here. So 1, 2, 3, 4, 5, right? So when nitrogen mixes, where does nitrogen need to have electron density? How many places? So it's either sigma bonds or lone pairs. So we have to add that in, right? It's either sigma bonds or lone pairs. So if we were to mix these up, we would find that we only need one bond and one lone pair. So on the side, just like ours up there, we have 1 and 1. So this is not connected. So this is our SP, right? That's our lone pair. That's on N. We see it up here. And then N needs 1 lone electron in order to bond a single bond. So it's SP. So these must also be 2p orbitals that are also unbound, right? So carbon has a p orbital that's unbound. So I'm going to gesture with my hands. So we have, if you look at the x, y, and z axes, right? You'll see that p orbitals, you have one p orbital going on the x, the y and the x, the y and the z axis, right? So the px is actually the orbital that overlaps. So we have what's called orbital overlapping. That is where a sigma bond comes from. So we'll sum all this up in one more sheet of paper. Nitrogen also has a sigma overlap, an overlap of electrons. That's where we have one lone and one coming in. The p electrons, though, what are they? The orbitals, if you remember, p orbitals are shaped like this. Right? They're shaped like this. So you have one that's going this way, one that's going this way, and one that's coming at you. So it looks like the x orbital is taken over. So we're going to have one that's going straight up and down from the carbon, and we're also going to have one that's coming right at us from the carbon. And these also have a lone electron in them, don't they? How about nitrogen? Same deal. One that's coming up, coming down, and he also has one that's coming straight at us, right? My drawings are not pretty. If you look at the text, it's much better. So what is a double bond? That is the attraction from, we have our YY unpaired 2p or unhybridized 2p orbitals. They kind of talk to each other this way. So it is an indirect attraction, so it's an indirect bond. Then we also have our two Z's coming right at you. These also have an attraction to each other. So that's how we get our triple bond. So I'm going to find another piece of paper here in this room. I know you think that I would have paper, but apparently it's just not something So let's sum up what we found. So this is going to be hybridization, summing it up. So we found that sigma bonds come from orbital overlap. Where do pi bonds come from? Indirect, unhybridized p orbitals. All right. We learned that also that, and this is where we're going to go real easy. This is going to make things so easy. Sigma bonds are from either orbital overlap, and then in order to count them, you have areas of electron density. And then we have the hybridization. So if we have two areas of electron density, the hybridization is sp. If we have three areas of hybridization, here's how it's easy. So it must be an S, and then what comes next? Two of the P's, right? Because picture the P block from the other one. It must, if we have electron density in three places, it's got to go 1, 2, 3. So S and two P's. So sp2. If we have four regions of electron density, it's going to be an sp3 because it has to involve the S and what's the next option? 3 of the P's. So real quick, we are going to do an example that involves an expanded octet. See, again, we're all doing this. So what about the rest, right? If we have an expanded octet, that means one example that they like to do is PCl5. So PCl5. So P is going to be in the center, and if we look at P, where's P at? P is right here. So it has 3s2, 3p3. So P is 3s2, 3p3. So it's going to look like this. And we're going to go up, up, up. Okay. So PCl5, if you took the time to do the Lewis structure and totaled it all out, I guarantee you it would look like this. We're going to total it out with the correct number of electrons. So how many electron dense regions, regions of electron density are on phosphorus in this example? There are 1, 2, 3, 4, 5. They're all sigma bonds. So I need 5 of these arrows pointing up and just being by themselves. 5 electrons that are unpaired. Recall that this is our 3s and this is our 3p orbital. But what do things in the third row have that's empty? If you're playing our game at home, you guessed 3D, you're correct. So everything in the third row or below can have an expanded octet. So we're going to note that down here. Everything in n equals 3 or below can have expanded octet. Right? So that means that they are not bound by the rules of expanding the octet. So let us see how we would do this. So I need 5 places to bond. So I'm going to have to promote this electron where? To this first box here. And then I will have 5 lone electrons pointing in the same direction. So let's do that. Let's hybridize. Let's mix orbitals. Because I need 5 that are pointing in the same direction. Okay? So I used this one. What about these? 1, 2, 3, 4. The 4 of the 3Ds. I didn't use them. So they actually just are empty. So these are my unhybridized 3D orbitals. But what is this called? If you're playing our game at home, you could probably guess. It's an sp3d. It's an sp3d. Now we have the places for the 5 sigma bonds to come in. These are unhybridized and they are open. So let's finish this chart, shall we? If we have 5 regions of electron density, what is it? sp3d. There's no more p's after 3, so it's sp3d. And lastly, what if we have 6 regions of electron density? S, and then you have 3 p's, so S, 1, 2, 3, P, and then D1, D2. So it is an sp3d2. Let's talk about shape as fast as possible. If we have 2 regions of electron density and they're both bonds, how far apart are they going to be spaced? What's the farthest apart 2 electron dense regions can be? It's the same as AB2, so it's going to be 180 degrees. How about 3? What's the farthest apart 3 electron dense regions can be? 120, so it's the same as trigonal planar. How about 4? 4 regions of electron density, how far apart can they possibly be? 109.5. How about 5? That's going to be our trigonal bipyramidal, so it's going to have a 120, a 90, and a 180. Remember the trigonal bipyramidal where we have our axial and equatorial positions? And then lastly, 6, which is our octahedral, that's going to have all 90 degrees. And 180 if you want to be picky, but 90 degrees would be would work for me. So hopefully this hybridization lecture helped a little bit. I know that this is probably the one that gets people the most, but it all boils down to this chart. But we did have to go through the weeds to figure out how to get this really easy chart and how to, how to get to that. So I will be bugging you all later. Thanks.